Hey everybody, today we will discuss asynchronous fault-tolerant computation. This work is by Tal Abraham, Dani Dolev, and myself, Gilad Stern. In general, we want to explore the limits of fault-tolerant computation in the face of an unbounded Byzantine adversary in an asynchronous setting. And our goal here is to explore how different thresholds on the number of Byzantine parties can affect which tasks we can and can't perform in this setting. So a little bit of general background about asynchronous fault tolerance. The famed FLP result showed that in an asynchronous network, if even one party might crash, every agreement protocol has a non-terminating execution. Now, an easy corollary here is that an adversary can cause every deterministic agreement protocol to just run indefinitely. On the other hand, there are randomized protocols that almost surely terminate, and by almost surely we mean with probability 1. In 1983, Michael Benol, Ran Canetti, and Oded Goldreich showed that any functionality has an almost surely terminating protocol with perfect security if n is greater than 40, where t is the number of parties the adversary controls. However, we have lower bounds for certain functionalities, for example, agreement, that show that those functionalities are impossible if n is less than or equal to 3t. Now, we want to close this gap somehow. So in 1993, Ran Canetti and Tal Rabin showed that there exists an asynchronous Byzantine agreement protocol for n greater than 3t. And a year later, in 1994, Michael Benol, Boaz Kelman, and Tal Rabin showed that there exists an asynchronous multi-party secure computation protocol for n greater than 3t. The problem is that both of these works had an annoying property, as they said, of a non-zero probability of non-termination. Now, BKR even provided a sketch of a proof that it is impossible to achieve an almost surely terminating asynchronous verifiable secret sharing if n is less than 40 in the face of Byzantine failures in asynchronous systems. So a little bit of background about what AVSS intuitively is. AVSS is a two-phase protocol, a share phase and a reconstruct phase, that tries to emulate the following ideal functionality. In the share phase, there's a designated dealer. It has an input S that we sometimes call the secret. And the first step is sending the secret it got to the ideal functionality. Afterwards, the ideal functionality sends a done message to every party, including the dealer. Afterwards, in the reconstruct phase, every party sends a ready message to the ideal functionality. And then the ideal functionality replies with the message it received in the first phase, in this case, S. Finally, every party outputs the value it received from the ideal functionality. So intuitively, there are three types of run to an AVSS protocol. The first type is where the dealer is non-faulty. It receives some value S as an input, sends it over to the ideal functionality, and then the ideal functionality sends a done message to every party and they complete the share protocol. Now, note that in this case, the only party here that heard anything about that value is the ideal functionality. So throughout the share phase, that value remains secret, hence the name. Then in the second phase, in the reconstruct phase, the ideal functionality will send that value to everybody and everybody will output that value. The second type of run is where the dealer is faulty and simply doesn't send any message to the ideal functionality in the share phase. And in that case, the ideal functionality won't send a done message, and then no party will complete the share protocol, and clearly not start the reconstruct protocol or complete it. Then the third type of run is where the dealer is faulty, but decides to send something to the ideal functionality. It doesn't have to send S, but it sends some value. In that case, the ideal functionality will send a done message, and then everybody will complete the share protocol, and then start the reconstruct protocol and complete it. Note that in the reconstruct protocol, the ideal functionality will send the message it received in the first phase, the message that the faulty dealer sent. So in this case, the faulty dealer has to commit to a value during the share phase that every party will then output in the end of the reconstruct phase. Now we can move on to the main results of the paper. The first one is a lower bound. For every epsilon between 0 and 1/2, and n which is less than or equal to 4t, there does not exist an almost surely terminating 1/2 plus epsilon correct, T-resilient Byzantine AVSS protocol. This teaches us something about optimal resilience for such protocols. Now, when we compare this result to BKR's result from 1994, first of all, this is a full proof. And secondly, it allows for some probability of error, whereas their result did not. Now, this is important because AVSS protocols today and the ones they used back then have some probability of error. This means that we managed to match the lower bound to the upper bound. Secondly, we have an upper bound result. There exists an almost surely terminating asynchronous fair Byzantine agreement protocol resilient to fewer than n/3 faulty parties. And note that n greater than 3t is optimal resilience for such protocols. Now, a fair Byzantine agreement protocol is basically a regular Byzantine agreement protocol, except it also has a fairness property as well. Now, fairness is as follows. All non-faulty parties output some non-faulty parties' input with probability 1/2 or greater, in addition to all of the other properties of Byzantine agreement. All right, so now for a formal definition of AVSS. AVSS is a pair of protocols, share and reconstruct. There's a designated dealer that receives some input S for the share protocol, and the reconstruct protocol has an output. An almost surely terminating 1 - epsilon correct T-resilient Byzantine AVSS protocol has the following properties if there are no more than T Byzantine parties. First of all, termination. If the dealer is non-faulty and all non-faulty parties participate in the share protocol, they all almost surely complete it. Secondly, if any non-faulty party completes the share protocol, then any non-faulty party that participates in it completes it as well, almost surely. And finally, if all non-faulty parties complete the share protocol and start the reconstruct protocol, they almost surely complete it as well. The second property is correctness. Once the first non-faulty party completes the share protocol, there exists some value R, such with probability 1 - epsilon or greater. First of all, if the dealer is non-faulty, R equals S. And secondly, every non-faulty party that completes the reconstruct protocol outputs R. Finally, the third property is secrecy. If the dealer is non-faulty and no non-faulty party has begun the reconstruct protocol, no adversary can gain any information about the secret S. More precisely, the adversary's view of the execution of a share protocol before some non-faulty party starts the reconstruct protocol is distributed entirely independently of this. So now we're going to go over an overview of the lower bound. We're going to say what exactly we're going to try to prove, and then how we're going to prove it. In the beginning of the setting, we have 4 parties, A, B, C, and D. D is the dealer. This means n equals 4 and t equals 1. But using standard techniques, we can extend this proof to any n and t such that n is less than or equal to 4t. The network is asynchronous. This means that messages can be delayed any finite amount of time. In order to prove our theorem, we will assume there exists an almost surely terminating AVSS protocol. We will show that it has an error probability of at least 1/2. This means that it cannot be correct 1/2 plus epsilon% of the time. In order to prove this result, we will use 2 attacks. The first attack is for a faulty dealer. D will send contradicting values to parties A and B. C will be slow. And with some non-zero probability of success, A and B won't notice that the values contradict. In that case, they complete the share protocol, they start the reconstruct protocol, and they must output something, but their values contradict, so it seems bad. Then, the second attack will take that non-zero probability of success and boost it to a probability 1 of succeeding. We'll show an attack for either party A or party B. And regardless of what the non-faulty dealer in this case shares, one of those parties can make the world indistinguishable from the previous attack conditioned on success. Now, if we look at party C, it doesn't know what to output. Party A and party B have contradicting values, and it can't decide. We will start by proving a helpful lemma. Observe crash world 0. In crash world 0, parties B and D are non-faulty. D has the input 0. Party C is non-faulty but slow for now, and party A is honest but curious. This means it acts entirely non-faultily throughout the share protocol, but it tries to gain more information than it's supposed to. On the other hand, observe crash world C. In crash world C, parties A, B, and D are non-faulty, and party C is faulty and crashed. The adversary told it not to send any messages. Now, the behavior of parties A, B, and D, as well as party C's behavior, being crashed, are entirely indistinguishable in both worlds. They act entirely non-faultily, and the dealer shares the value 0. This means that the worlds are indistinguishable to the involved parties. Now, if we observe crash world C, all the non-faulty parties, including a non-faulty dealer, are participating in the protocol. So we know the share protocol must complete. On the other hand, if we look at crash world 0, these worlds are indistinguishable. So the parties must complete the share protocol in this world as well. Now, look at party A's information throughout the protocol. Party A receives messages from D and messages from B. And those messages must not indicate in any way which value is being shared. That is, they must be compatible both with the value being shared being 0 and the value being shared being 1. If we say that MAB are the messages that A and B exchanged, and MAD are the messages that A and D exchanged, then every possible such set, MAB and MAD, must be compatible both with 0 and 1. The same argument can be said for sharing 1 or for party B as well. Now we can describe the first attack. So first of all, observe these two worlds, share world A and share world B. In both of these worlds, parties A, B, and D are non-faulty. Party C is faulty and crashed. The adversary told it not to send any messages. And the only difference between the worlds is that in share world A, the dealer has the input 0, and in share world B, the dealer has the input 1. Note that, as we've shown in the previous lemma, in both of these worlds, parties A, B, and D must complete the share protocol. Now we'll move on to look at this hybrid world. So in share world hybrid, the dealer D is faulty, parties A and B are non-faulty, and party C is non-faulty but slow for now. Now, in this world, D tries to execute the following attack. It tries to send A messages that are compatible with sharing the value 0, and B messages that are compatible with sharing the value 1. The way it exactly does it is as follows. It first of all guesses A and B's randomness, then it guesses the messages that they're going to exchange between each other, and then finally it tailors its 0 messages and its 1 messages to its 2 previous guesses. Now, 2 important things to note here. First of all, whichever messages A and B exchange between each other, they must be compatible both with sharing the value 0 and with sharing the value 1. That's what we've shown in the previous lemma. Now, this means that there must exist some set of 0 messages that D can send to A that are compatible with the messages it's going to exchange, with the messages it guesses it's going to exchange. The same goes for party B. Secondly, if D manages to make those guesses correctly and manages to tailor its 0 messages and 1 messages, then from A's point of view, this run could have taken place in share world A. Its entire worldview is consistent with sharing the value 0. And similarly, B's worldview is entirely consistent with share world B. It could have happened there. And in both of these worlds, parties A and B always complete the protocol. Now, if we summarize the implications of the first attack, first of all, we found out that if D guesses A and B's randomness, then they will complete the share protocol. Now, when that happens, A and B are at a disagreement about the output value, and C can't help. It didn't receive any messages from the dealer. Now, this might seem bad, but this only has some non-zero probability of success. If we recall, D needs to guess A and B's randomness, and that might happen with a tiny probability, and certainly not with a 1/2 plus epsilon probability. Now, the second attack will take this attack and boost its probability of success to be 1. Now we will describe the second attack in the case that D shares a value 1. If D shares a value 0, a very similar attack can be executed, reversing the roles of parties A and B. Now observe Reconstruct World 1. In that world, parties B and D are non-faulty. Party C is non-faulty but slow for now. Party A is faulty but acts non-faultily throughout the share protocol, and D shares a value 1. As we've seen before, in this case, parties A, B, and D must complete the share protocol. Once A completes the share protocol, it does the following things. It samples new messages. It will report from this point on A and D exchanged. The way it will do that is in the exact same way as party D samples messages in the previous attack. Now, if we recall the previous attack, party D might fail because it fails to guess A and B's randomness in the messages they exchange. A, however, in this world already knows what messages it exchanges. So it can sample 0 messages which are compatible with the messages it exchanges with B, with probability 1. And in that sense, it manages to emulate the first attack conditioned upon success. Now we will move on to describe the reconstruct phase of these runs. In Reconstruct World Hybrid, parties A, B, and C are going to communicate freely, and party D is going to be silent. Note that in this world, party A has a history consistent with the value 0, and party B has a history consistent with the value 1. Since all non-faulty parties participate in the Reconstruct protocol here, they must complete it as well. Now let's move on to look at Reconstruct World 1. In Reconstruct World 1, party D is going to be slow for now, and party B and C are non-faulty, and party A is going to act like a non-faulty party with its new history it sampled. Note that these worlds are indistinguishable. Parties A, B, and C are communicating freely. A has a history consistent with the value 0, and B has a history consistent with the value 1. This means that in this world, A, B, and C must complete the reconstruct phase as well. In summary, we've shown 3 indistinguishable worlds. Reconstruct World 0 and Reconstruct World 1 are indistinguishable from Reconstruct World Hybrid, conditioned upon D's success. Now, in Reconstruct World Hybrid, all non-faulty parties start the Reconstruct protocol, and thus they must complete it as well. Note that since these worlds are indistinguishable, all parties' actions must be the same in the 3 worlds. Now, if C outputs 0 with probability less than or equal to 1/2 in all 3 worlds, validity is broken in Reconstruct World 0, since the non-faulty dealer shared 0, and that means C must output 0 with probability 1/2 plus epsilon at the very least. On the other hand, if C outputs 1 with probability 1/2 or less, validity is broken in Reconstruct World 1 for the same reason. This concludes our proof. So is all lost for functionalities that use AVSS? One common use of AVSS today is implementing common coins, and current common coin constructions have usually one of 2 shortcomings, either a non-zero probability of non-termination, which stems from using AVSS, which has a non-zero probability of non-termination, or just completely failing about a number of times because they use a variant of AVSS that can completely fail about a number of times. One upper bound shown in the paper is the following upper bound. An asynchronous, almost surely terminating epsilon-biased common coin has the following properties. First of all, termination. If all non-faulty parties participate in the protocol, they almost surely complete it. And in addition, if some non-faulty party completes the protocol, every non-faulty party that participates in it completes it as well. Second property is correctness. For every B, which is either 0 or 1, the probability that all non-faulty parties output B is no smaller than 1/2 minus epsilon. In addition, all non-faulty parties that complete the protocol output the same value. Now, the upper bound is as follows. For every epsilon between 0 and 1/2, there exists an asynchronous, almost surely terminating epsilon-biased common coin protocol resilient to fewer than n/3 Byzantine corruptions, which is optimally resilient. So using weaker common coins, we know how to construct Byzantine agreement protocols. Now, using that stronger common coin, we show in the paper how to construct a fair Byzantine agreement protocol. So fair Byzantine agreement has the following properties. First of all, termination. This is the same termination as the common coin's termination property. First of all, if all non-faulty parties participate in the protocol, they almost surely complete it. And secondly, if some non-faulty party completes the protocol, every non-faulty party that participates in it completes it as well. Secondly, fair validity. So the first part is validity. If all non-faulty parties have the same input, they output that value. And the second part is the fairness part. With probability at least 1/2, all non-faulty parties output some non-faulty parties' input. Finally, correctness. All non-faulty parties that complete the protocol output the same value. The construction of the paper proves the following theorem. There exists an asynchronous fair Byzantine agreement protocol resilient to fewer than n/3 Byzantine corruptions. Now, this is optimally resilient, which can be seen because this is also a Byzantine agreement protocol. And that's the optimal resilience for Byzantine agreement protocols. Now, it is important to note that every Byzantine agreement protocol is a fair Byzantine agreement protocol in the case of binary agreement. So this extra fairness property is only interesting in the case of multi-valued agreement. We can compare this result to similar results dealing with multi-valued Byzantine agreement. In 2016, Mustafawi et al. Showed an intrusion-tolerant Byzantine consensus protocol. This is basically regular consensus, except all non-faulty parties either output some non-faulty parties' input or the output bottom. The issue is that if the non-faulty parties don't start with the same input, the adversary can always cause them to output bottom. Another approach seen by Abraham et al. In 2019 is a validated Byzantine agreement protocol. This protocol uses threshold signatures and an external validity function suggested by Kashin et al. In 2001. The function is an external function. Every party can run it. And with that function, they can check whether an input is valid. This protocol is basically fair Byzantine agreement, except all non-faulty parties also output a valid value. Our work can be seen as an information theoretic analog of this work. Just to recap, these are our main results. First of all, a lower bound. For every epsilon between 0 and 1/2, and n, which is less than or equal to 4t, there does not exist an almost surely terminating 1/2 plus epsilon correct T-resilient Byzantine AVSS protocol. Secondly, an upper bound. There exists an almost surely terminating asynchronous fair Byzantine agreement protocol resilient to fewer than n/3 faulty. Thank you very much.